Good morning, all of you. In today's session, I am going to discuss about digital signal processing. Digital signal processing is common today. Everybody of us is directly or indirectly related to DSP. It is having wide applications. So in today's session, let us see the review of discrete signals and systems. The overall presentation outline of this we can sum up like this. Introduction to DSP, principle and operation of DSP, advantages and disadvantages of DSP, the applications of DSP and conclusion. So we are all familiar with this term that digital signal processing. This DSP is having wide applications in various fields such as communication, medical imaging, radar, forensic, and much more. What is signal processing? In very simply, we can say signal processing is nothing but processing any signal for extracting information. So, processing any signal means we can process analog signal or digital signal. When we are processing signal, especially digital signal, with the help of a computer, we can say it is digital signal processing. Then, what is a digital signal? What is analog signal? Signal, how we can define? Any physical quantity that varies with time and carries some information, we can say as signal. Then what is processing? The various operations that we can perform to extract some information, we can say as processing. Here we are interested in digital signal processing. So the word digital indicates that the processing is done using digital computer, or even we can process it using special purpose digital hardware. We can classify signals such as based on the number of independent variable. Again, we can classify signals depending on certainty. Again, we can classify based on repetition nature, etc. So these are the ways that which we can classify signals. Now, based on independent variable, we can classify signal as continuous or discrete. A continuous time signal, it is represented as x of t. For example, the speech signal is an example for a continuous signal. Here, the continuous signal we can represent with a sine wave like this you are seeing right now. This continuous signal can be sampled at regular interval, which is known as a discrete signal. Discrete signal is represented by x of n. Again, we can classify signal as one-dimensional signal, two-dimensional signal, and multi-dimensional signal. A one-dimensional signal means that signal depends on a single independent variable. Example is speech signal. Whereas a two-dimensional signal, that is a function of two independent variables, example image. And a multi-dimensional signal is a function of m independent variables in time. So example, a video signal where we can have red, green or blue are the variable, different colors. Now again, depending on certainty, we can classify signal as deterministic signal or random signal. A deterministic signal we can express using mathematical formula. For example, x of t is equal to Vm sin omega t. Any time, what's the value of the signal we can predict. That's a deterministic signal. Whereas a random signal, we cannot predict what time the value of the signal at any instant we cannot predict. Lightning is an example for a random signal. ECG. Again, we can classify signal based on the repetition nature. That is periodic signal and non-periodic signal. So these are some of the classifications of signals. Further, we can classify signal as even signal and odd signal. That is, this classification, even signal and odd signal, that classification is based on reflection. So we can check whether a given signal is even or odd. What's the condition? For an even signal, x of t is equal to x of minus t for all t. Similarly, discrete, x of n is equal to x of minus n in the case of discrete. So this is, if this condition is satisfied, then that signal is even signal. For an odd signal, if the signal is odd, then x of t is equal to minus x of minus t, or we can say in case of discrete, it will be x of n equals minus x of minus n. We are interested in digital signal processing. When we are applying a digital signal processor or a computer for processing the signal, then that process, we know it is digital signal processing. But in and around us, if you analyze, most of the signals are analog in nature. So the first step is we have to use an analog to digital converter, ADC. What's the purpose? The purpose is to convert the analog signal into digital signal, zeros and ones. This process is done using an ADC. Then we can process this digital output that is coming out from the analog to digital converter using various processors, digital signal processors we can use. And we can again convert the digital signal back into analog signal, and we can utilize the information for various applications. What is the advantage here is we can remove various distortions that arises at the time of capturing information, or various noises that are incorporated during transmission. What is the need for signal processing? So we have discussed that when a signal is transmitted from one point to another, there is every possibility of deformation or contamination of this information by external noise. Therefore, to retrieve the original signal at the receiver, we can use suitable filter. That is, the signal can be processed to obtain a pure signal. We know that signal processing can be broadly classified as analog signal processing and digital signal processing. So we are interested in digital signal processing. So let us focus our attention about DSP, digital signal processing. This is the block diagram of a DSP, digital signal processing. So first here, the analog signal is applied to the sample and hold circuit, and it is applied at the input of ADC, analog to digital converter. Then we can use chain of filters, I mean digital filters. And our digital signal is now ready for application. This digital signal processing is a wonderful area, and why it is so much in demand, or why it is so versatile, because it is having, or it is sharing boundaries with many areas such as science, engineering, and mathematics. DSP is having an overlapping borders with many areas. So that is the beauty of this subject. These overlapping areas are analog electronics, digital electronics, decision theory, analog signal processing, probability and statistics, numerical analysis, and communication theory. These are all is sharing boundaries with DSP. So becoming a master in DSP is a Herculean task. One has to be a master in all these areas. Then only he can become a master in digital signal processing area. In DSP, I said we are using filters. This is exactly digital filter. In digital signal processing, if you want to filter out, we have to apply digital filter. Analog filters cannot be applied in this area. So mainly there are two types of digital filter. What are they? Finite impulse response filter, that is FIR filter, and infinite impulse response filter, IIR filter. We are in subsequent chapters, we are focusing much on FIR and IIR filters. How we can design all this. What are the advantage of this digital filter or DSP filter? They are immune to environmental changes. They are immune to noise. And it is having good efficiency. So these are some of the advantages of DSP. When we come, what are the advantages of DSP? DSP is having many advantages, such as accuracy, flexibility, ease of operation, multiplexing, storing, etc. And needless to say, we are all knowingly or unknowingly using DSP in various fields such as image processing, consumer application, cellular mobiles, in speech and music, and much more. To be very frank, there is no life without DSP today. And there are some certain limitations for DSP, such as loss of information due to when we take samples of signals at interval, we are taking samples of signals, and this may create some information loss. Again, there can be quantization error. Sampling and quantization we are doing, some error or some error can occur due to this sampling and quantization effect. We are all familiar with the microprocessor, and there is difference between a microprocessor and digital signal processor. A microprocessor with its limited speed can be applied for low speed applications, whereas DSP is meant for fast and real-time applications. And most DSP processors use modified Harvard architecture. And in comparison with a microprocessor, it uses Van Neumann architecture. So this is when we compare DSP processor with the microprocessor. There are various DSP processors such as TMS 320C1X, TMS 320C2X, TMS 320C5X, etc. These are all 16-bit. For 32-bit also are there, TMS 320C3X, TMS 320C4X are all 32-bit. We can refer various textbooks such as Openium, Prakyas, and Ramesh Babu, Salivahanan. All these textbooks you can refer for information. Even you can refer web reference. I am listing here all the web reference where you can explore more. Let us now see the various ways of representing discrete time signals. I'm just brushing up the things that is essential for proceeding deep into DSP. That is the representation of discrete time signals. The major representation are graphical representation, again functional representation, tabular representation. This is a graphical representation of a discrete time signal. Graphical representation of a discrete time signal. We are interested in discrete. So a discrete signal is represented by x of n. Here you can see at the origin it is represented as x of 0. Then we have both directions, and the amplitude are represented by a discrete line, and at various levels, x of 0, x of 1, x of 2, the amplitude is decreasing with respect to the time n, and it is going negative. The negative amplitude you can see it is represented downwards. Similarly, x of minus 1, it is having an amplitude, positive amplitude, and this type of a representation is a graphic representation. Again, this is also a graphical representation of discrete signal. Different ways we can have the signal represented in graphical representation. For example, a discrete signal x of n with values x of minus 1 is equal to 1, it is given. For example, x of 0, it is equal to 2, x of 1, it is 1, x of 2, 0.5, x of 3 is equal to 1.5. You can represent this one graphically the same way like this. At different values at the origin, what is the amplitude? For example, x of minus 1, you have to take a unit and represent this as 1. At the origin, it is 2. Like that, we can represent this example in graphical representation. This is another way of representing is known as sequence representation. For example, here x of n is equal to, they have given x of n is equal to 1, 2, 2, 0.5, 1.5. Here, this arrow sign indicates the origin. That means at x of 0, the amplitude value is 2. And left side it is 2 samples. Right side also it is with respect to the origin, 2 samples to the left and 2 samples at the right. So this type of representation is a sequence representation. A signal, a unit step signal in graphical representation is expressed like this. Here, unit step is represented as u of t is equal to 1 for t greater than 0. For all values of t which is greater than 0, it will maintain a level of 1. This is what is a unit step. Again, in the figure B, it is a delayed unit step that is represented as u of t minus a. That means u of t minus a is equal to 1 for t greater than A, 0 otherwise. So unit step signal we can represent, and it's maintained u of t is equal to 1 for t greater than 0. A unit ramp is represented as R of n is equal to n for n greater than equals 0. A unit ramp signal. A unit impulse is represented as delta of n is equal to 1 for n equals 0. And for all other values, it will be 0. It means 0 for n not equal 0. This is a unit impulse. A unit impulse signal is this. This is a graphical representation. At delta of n is equal to 1. Delta of unit, if you take the slope of this one, it is 1. That is what it is the meaning of unit impulse. Delta of n is equal to 1 for n equals 0. And 0 for n not equal 0. Similarly, we have exponential signal. An exponential signal can be represented as x of n is equal to a power n for all n. This is the representation of graphical representation of an exponential signal. Here it is represented as y equals 2 power x. If you put x value, by changing x value different, we can have different values for y. There are various operations that we can perform on signals: shifting, time reversal, time scaling, scalar multiplication, and signal multiplier. All these are the various operations that we can perform on signals. In this unit, we are studying the widely used transform, that is Z transform. Basically, we should know what is the purpose of, or what is the need of a transform. Then we will move on to Z transform. What is the need for transform? Or why we have to apply transform in a particular situation? The answer for this question is, first one is for mathematical convenience. Mathematical convenience means if you are working in a time domain signal, there we have to apply convolution operation. If you apply convolution operation, it is a tedious process in time domain signal, in time domain area. Whereas this computationally difficult operation of convolution can be easily applied in frequency domain by just multiplication operation. That means the tedious process of convolution in time domain can be easily achieved in frequency domain. That means we need to have a transform that is switching us from the time domain signal to frequency domain. So this is, if you can do that, the mathematical convenience can be achieved. We can easily compute it. Computation time will reduce. So that is the first need for a transform, mathematical convenience. Not only mathematical convenience. The second advantage or the second need is we can get more information. We can get more information from the signal or from the input. For example, now you are watching two people who are standing and observing, who are standing and watching white light, which is passing, and both are, this person 1, this is person 2, both are observing it. The person 1 is standing before a prism and person 2 is standing behind or after the light is passing through the prism. Both are observing same input, white light. But person A can understand it only as white light, whereas person B can observe the various constituent of this white light, violet, indigo, blue, green, etc. The spectrum of colors he is able to see because he is using a prism. In place of this prism, we can keep a transform. That means what a prism is doing for white light, the same thing is doing transform in different domain. It can be time domain, can be frequency domain, etc. So irrespective of the domain, if you want more information, then we can go or we can get the help of corresponding transforms. There are large number of transforms available. So the two need for transform, first one is for mathematical convenience and second need is for getting more information. So what is transformation? It is nothing but a mapping from one space to another. There are different transforms such as Fourier transform, Laplace transform, Hilbert transform, Hartley transform. All these Fourier transform, Laplace transform, Hilbert transform or Hartley transform are to convert differential equation to an algebraic equation. Similarly, there are many more. Discrete Hartley and Fourier transform can be used to convert the convolution integral into something more easily calculated and we can have many more transforms. Again, here there is another transform that is known as Walsh transform. This Walsh transform is very useful in image processing. Then we are coming across the term mathematical model. What is a mathematical model? The mathematical model is nothing but the system of equations describing a system is known as the mathematical model of that system. It is challenging and it is difficult or mind-blowing to solve the system of equations in time domain. For this purpose, Laplace invented a tool to transform the differential equations into algebraic equations, provided that these equations are linear. So that is the use of Laplace transform. There are the term discrete time functions. These discrete time functions and systems, we have the Z domain. The Z domain is nothing but the discrete S domain. Which can be expressed as Z is equal to exponential S into Ts. What is this Ts? It is the sampling time. And S is nothing but J omega. In this unit, we are focusing our attention on Z transform. Very important area, Z transform. So we now know what is the need of transform. I said mathematical convenience and obtaining more information. So we are having no doubt about the need of transform. The first transform we are applying or we are studying in unit 1 is Z transform. This transform is used in DSP and it can be expressed using mathematical equations. This Z transform is a mathematical tool that is commonly used for the analysis and synthesis of discrete time control systems. Using this Z transform, we are able to transform a time domain signal into frequency domain signal. This Z transform is a generalization of Fourier transform, because Fourier transform, we know it will not converge on all sequence. So we can go for Z transform. How we can define an Z transform? Z transform is of a sequence. Z transform of a sequence x of n can be defined as x of z is equal to sigma n is equal to minus infinity to infinity x of n z power minus n. This is the definition or mathematical representation of an Z transform. This Z transform can be one-sided Z transform or it can be two-sided. You can see the limit here minus infinity to infinity. If it is 0 to infinity, it is a one-sided Z transform. If it is minus infinity to infinity, it is two-sided. Then we must know the Z plane that is associated with Z transform. Here you can see an imaginary part and a real part, x and y axis. The x axis represents the real part and y axis represents the imaginary part, IM. And we are drawing a circle having radius z is equal to e power minus j omega. So this is how the z plane of the transform can be represented. The Z transform of a discrete time signal is defined by the power series. What is Z here? The Z is a complex variable. And it transforms the time domain signal x of n, into x of z. What is x of z? A complex variable. So this transform is extensively used for the conversion of time domain signal and this is a transform of a signal x of n can be denoted as x of z is equal to is a transform of x of n. Now we know x of n represents the discrete signal. Now suppose x of n, if you want to obtain back, what you have to do? You have to take the inverse is a transform of x of z. That is what this is all about. X of n is a transform x of z. So if we take inverse transform of x of z, we will get our discrete signal. And there is ROC region of convergence. Since Z transform is an infinite power series, it exists only for those values of Z for which the series converges. That means region of convergence of x of z is the set of all values of z for which x of z attains a finite value. Here there is a numerical. It is mentioned as x of n is equal to 1, 2, 5, 7, 0, 1. You have to apply is a transform for this particular sequence. How do we do? So this is a one-sided equation. You can see they have not given any arrow mark here. If arrow mark is mentioned, that represents the origin. If arrow mark is not available in this particular problem, there is no arrow symbol. That indicates the starting element is the origin. Starting element represents the origin. That means here x of 0 is equal to 1. X of 1 is equal to 2. X of 2 is equal to 5. X of 3 is equal to 7. X of 4 is equal to 0. X of 5 is equal to 1. So we can apply here in the transform mathematical representation. We know x of z is equal to sigma n is equal to 0 to infinity. X of n z power minus n. This is one-sided sequence. So limit is from 0 to infinity. So here we can apply that x of z is equal to x of 0 into z power 0 plus x of 1 z power minus 1 plus x of 2 z power minus 2 plus x of 3 z power minus 3 plus x of 4 z power minus 4 plus x of 5 z power minus 5. Now in place of x of 0 you can substitute 1 from the given data. X of 1 it is 2, x of 2 is 5, x of 3 is 7, x of 4 is 0 and x of 5 is equal to 1. When we apply this, we can further simplify it and write our x of z as 1 plus 2 z power minus 1 plus 5 z power minus 2 plus 7 z power minus 3 plus 1 into z power minus 5. For this particular one, what is the ROC? ROC is the entire z plane except at z is equal to 0. Isn't it? Because when z becomes 0, it is not converging. Because 2 z power minus 1 it is there. You can write it as 2 into 1 by z. There you apply 0, it becomes infinity. So all these values, it won't converge. All the values it will converge except at z is equal to 0. So ROC we got. So that is the importance and that is how we have to apply ROC in a particular problem, and we can check for which all values it is becoming infinite and what all values it is converging. Similarly, we can apply the same for this particular problem. Here they have mentioned the origin as 5. So x of 0 is equal to 5 here. The same we can apply here. We can find out the z transform. So this is the problem. Here it is two-sided sequence. So that's what x of z is equal to sigma n is equal to minus infinity to infinity. X of n z power minus n. So we can have here there are two left side sequence with respect to origin and 3 right side sequence. So we can substitute in this equation and we can apply and find out the z transform of the given problem as z square plus 2z plus 5 plus 7z power minus 1 plus z power minus 3. And we can, of course, write the ROC. Here also the entire ROC is the entire Z plane except Z is equal to 0 and Z is equal to infinity. Again, a number of problems on Z transform have been simplified here and ROC has been obtained. We can find the Z transform of an impulse function. An impulse function we know delta of n is equal to 1 for n equals 0. We can apply Z transform for impulse function. Z transform of x of n is equal to 1 by 2 whole power n u of n is another example which is simplified here. And the corresponding ROC we can obtain. Again, Z transform of unit step. So different possible questions are solved here. We can have the properties of ROC. Properties of region of convergence. The ROC cannot contain any poles. If x of n is a causal sequence, then ROC is the entire Z plane except at Z is equal to 0. These are the properties of ROC. If x of n is an infinite duration, two-sided sequence, then the ROC will consist of a ring in the Z plane, bounded on the interior and exterior by a pole. Again, the ROC must be connected region. Again, we can have the properties of Z transform. There are various properties for Z transform, such as linearity property, very important property, linearity property of Z transform. That is, if x1 of Z is equal to Z transform of x1 of n, and x2 of Z is equal to Z transform of x2 of n, then Z transform of a x1 of n plus b x2 of n is nothing but a x1 of Z plus b x2 of Z. This is known as linearity property. The linearity property we have to state and prove it. The proof of this linearity property is explained here. Again, we can have time shifting property. Time shifting property says that if x of Z is equal to Z transform of x of n, then Z transform of x of n minus m is equal to Z power minus m x of Z. This is known as the time shifting property. That means if input is shifting with respect to a time function, then corresponding Z transform is exponentially changing with respect to x of Z. So, time shifting property of Z transform is stated, and it is the proof of this time shifting property is explained here. Again, we can have multiplication property. if Z transform is multiplying with a power n, that is, if x of z is equal to z transform of x of n, then z transform of a power n x of n equals x into a inverse z. This property is stated and proved here. Again, we have time reversal property of Z transform, which is statement if x of z is equal to Z transform of x of n, then Z transform of x of minus n is equal to x into Z inverse. So we have come across different properties of Z transform. Suppose we have Z transform and we need the original sequence, then we have to apply the inverse Z transform. The inverse Z transform we can obtain using different methods. These methods are known as long division method, partial fraction method, residue method, convolution method. So if you want to apply inverse Z transform, we can go for different method to obtain the inverse Z transform. What is long division method? Here, a power series expansion is obtained by long division method. Let us see a problem to understand how we can apply long division method. For that, I am taking this particular problem. Find the inverse Z transform of x of z is equal to z plus 0.2 divided by z plus 0.5 into z minus 1 for modulus of z greater than 1 using long division method. So we are applying here the long division method technique. So we have written and keep on dividing. And we are obtaining this sequence of steps explained here for finding the inverse Z transform. So we are finally getting back our inverse Z transform as Z power minus 1 plus 0.7 Z power minus 2 plus 0.85 Z power minus 3 and 0.775 Z power minus 4. So there are different numericals I have kept here for applying inverse Z transform. All these are solved here. An inverse Z transform using MATLAB also is explained in this slide. We can find out the same in MATLAB, which is simpler than manual calculation. And in this unit, there is another term that is known as system function. What is system function? The output of a linear time invariant system to an input sequence x of n can be obtained by computing the convolution of x of n with unit sample response of the system. This relation can be expressed as y of z is equal to h of z into x of z. What is y of z? Y of z is the z transform of the output sequence, y of n. Y of z is the z transform of the output sequence, y of n. X of z represents the z transform of the input sequence x of n. What is h of z? Is a transform of h of n, which is nothing but the unit sample sequence. When a system is described by a linear constant coefficient difference equation, which is represented as y of n is equal to minus of sigma k is equal to 1 to n ak y into n minus k plus sigma k is equal to 0 to m bk x into n minus k. From this, the system function can be determined by computing the Z transform on both sides. We have just explained the computation of Z transform. So apply this Z transform on this equation, we are getting y of z. From this, we can compute the system function, that is nothing but y of z by x of z, just mathematical manipulation. We can get it. So this is the general form of a system function, which is described by a linear constant coefficient difference equation. So this is another important area in this unit. We can apply this system function for solving different problems. I have computed different solution here using system function, and I am keeping all this for your reference. The answer is also given there. You can kindly go through all those regarding system function. Another important topic in this unit is the initial value theorem that is associated with Z transform, the initial value theorem. That is, if x of t is a transform x of z and x of 0 is equal to limit z tends to infinity x of z, then x of t is equal to limit z tends to infinity z transform of x of z minus z transform of x of 0. This initial value theorem statement, and it is the proof of the initial value theorem, is explained in this slide. Again, we can have the final value theorem, and the proof for this final value theorem is also stated here. So, through this session, I tried to explain the various steps that we can apply in digital signal processing. We have started from the representation of various signals. We have come across the need for transform. We focused on Z transform. We simplified various numericals on Z transform, the region of convergence, the properties of ROC, the properties of Z transform, the initial value theorem, final value theorem, the system function, and many more. Let us conclude with the famous Robert Frost statement, that is, the woods are lovely, dark, and deep, but I have promises to keep and miles to go before I sleep. Thank you.